Hey everyone, today is June 11th. Welcome to the SIG Instrumentation biweekly meeting. It looks like we have 4 items on the agenda. Frederick, do you want to take the lead on?
Yeah, so I think this is something that's actually been in our backlog for quite a long time, and we just had not had a chance to discuss it. I think the kind of summary of this issue is currently the path of logs on disk only contain name and pod name, namespace and pod name, and not and pod UID, but not namespace UID, if I remember correctly. And kind of the problem here was that just like pod UID, it's potentially possible to have clashes with namespace names as well. It's unlikely, but it can happen. And kind of the proposal that was proposed here is simply to add namespace UID as well, to make sure there cannot be collisions. So yeah, this seemed pretty reasonable to me, but we had never discussed it. So just kind of was wondering what other people were thinking.
What is this going to break if we change this?
So my understanding is we cannot break the existing paths. We would have to make them additive, and then potentially in the future deprecate the current ones. But I think David would be better to answer that.
Yeah, I think we would have to symlink a bunch of stuff. We've done this sort of thing before, if I recall. I haven't taken a look at this.
So in general, this seems pretty reasonable to me. So if folks could maybe, I mean, we don't have to discuss it at length here, but if folks could maybe read through the issue and comment what they think, then maybe we can take this to SIG Node and discuss it.
Yeah, I think that sounds reasonable. Is it okay if I sign you up, David, for this? I feel like you probably have.
I will bring this up at SIG Node.
Okay,
so you
awesome.
can put my name down.
I will.
Thank you. That was already it for that item.
Okay. The next thing is the API call latencies SLO. We were actually just talking about something related to this, but so currently scalability defines a bunch of SLOs on the API server, and these SLOs are heavily asterisked, which means that like basically we are guaranteeing that our response rates are going to be at a certain speed, a certain percentage of the time. Unfortunately, we can't actually guarantee any of these things because it is possible for people to configure arbitrary webhooks. So the idea was whether or not it would make sense to partition request metrics in such a way that basically allowed us to actually make guaranteeable claims, like for instance by having something like internal API server request processing time.
Correct me if I'm wrong, but isn't this SLO primarily just used to gate Kubernetes, whether Kubernetes releases go out or not?
It is, well, it's used for scalability tests.
Yeah, So to me, it sounds like then if you have like webhooks that may interfere with this metric, then you have to adjust that SLO accordingly when you offer Kubernetes as a service or whatever. Like you're still actually interested in serving, actually interested in the entire time it takes for you to serve your users, right?
Yes, but these, if you look at the top level of that directory, then you will see a SLOs.markdown. And these are not like gating releases. These are user-facing SLOs. Like these are like, this is what we are saying, we are guaranteeing a user. Which doesn't make sense because we can't guarantee this.
Exactly. I think that's kind of the problem, and that's something we need to fix. But I think segregating the metrics is a possible solution. I personally don't think it's the solution that we should go with. I think we should just change the wording on that and say, this is our guarantee. If you do not have webhooks, you need to think about what overhead a webhook introduces when you guarantee something to your users.
I mean, currently it's impossible to know how long an internal request takes in the API server, right? Like, I mean, we have webhook latency metrics and we have request metrics, but they're not really joinable, right? Like, you can't really.
What's the actual problem that we're trying to solve with that? Like,
we can internally define what the software that we are responsible for is actually doing, right? Like the thing that we are promising is like, we are promising things that are like outside the scope of things that we can promise, right? Like we should not promise things that.
But if webhooks are configured, users are still gonna experience what they experience, right? And that is still correct to alert on. But I do agree with you that like we need to have a mechanism to say, wait a minute, the requests did take this long, but it was because of the webhooks and not because of something API server. That's what we're trying to answer, right? So typically that is done with, or the way I've seen this done is with like histograms for the outgoing metrics that goes to the webhooks. And that is totally something that you could inhibit API server alerts, for example, if that particular alert is firing. Does that make sense? I mean, I don't know if other monitoring systems have this kind of capability, but in Prometheus, for example, you would say, okay, alert for webhook responses taking long. If that's firing, do not actually notify me about API server latency high, because I know that that's going to be high because of the webhooks being high.
It gets kind of complicated though when you have a lot of webhooks.
I mean,
because
yeah,
they're
they're
cumulative latencies, right? Like you can literally have hundreds of webhooks. So like you can actually be in the situation where one webhook is not alerting because the latency is actually quite reasonable for that webhook, but the aggregate total of your webhook processing time is extraordinarily high.
You could say the same for any aggregated API, no? Like you like if you have an aggregated API, we also track the entire the latency for that. And it could take arbitrarily long.
Yeah, for aggregated API, yeah, because it's
it's entirely independent.
Yeah, different API server.
Yeah. So I mean, what you could argue that that's equally as much a problem as webhooks, which I guess I agree with.
But we have component in our request metrics, and that should give you whether or not the endpoint is aggregate. So it's actually not the same, because we can actually distinguish the two right now.
Okay.
I mean, if people look, we have these publicly published SLOs with asterisks, and I mean, we can do the internal thing, but I don't okay, if there's an alternative to doing internal processing time, I'm receptive to it. I'm not sure that, at least I'm not understanding an alternative if you're suggesting one.
I mean, as I said, I actually don't think there's anything wrong with this. I just think that we cannot promise it in the way that it is stated there right now. Like we're coming from the same direction, right? But I'm saying, because people can customize their Kubernetes in various ways with webhooks, that does make it a custom experience, and they need to figure out what the SLOs for that is. And kind of a standard Kubernetes without any webhooks, this is what we can guarantee. And everything else you're going to need to figure out.
I do think it's all right to have high-level SLOs and then per component SLOs. So, I think it's reasonable to have metrics at different levels, but I agree with the sentiment that we should make sure that we're measuring something concrete and meaningful.
I would like to be able to tell, in the case that a Kubernetes cluster is not performing to some stated latency metric, if this is because of Kubernetes or not because of Kubernetes. I mean,
okay, so you brought up the example of you wouldn't know which webhook is the origin of the problem, right? Potentially, that's
yeah. There could be not a single webhook that is responsible for it. Yes.
Yes. So let's say we did have the metric that kind of captures the latency without webhooks. That's kind of what I understood you were
internal processing
proposing. Now, what would be the next step that you're for actually investigating this? You would still need to figure out which webhook or which combination of webhooks is actually causing this, right? Ultimately, you're still trying to resolve the problem, no?
I mean, maybe then we just need a dimension, right? Like internal or webhook processing time, right?
Yeah, I mean, I think that makes sense.
Yeah, and then you can join the two.
We kind of, if I'm understanding you correctly, we kind of run into the same problem as we do with like CRDs or something, where we can essentially now have an arbitrary amount of metrics added because it's dynamic.
But yeah, in this case, we just make a binary. It's a binary thing, right? Like it's either a webhook, part of the webhook processing time, or it's the internal API server processing time, right? And then if you sum the two, then you have the total request processing time.
So are you saying, okay, you're just trying to make the jump of, okay, I don't need to investigate anything in the API server. I know the problem is in some combination of webhooks.
Yeah, you know that it's in some combination of webhooks. You know that the cumulative webhook processing time for this specific endpoint was greater than what you expected. You don't like. There can be any n number of configurations of webhooks for any given endpoint, and that's going to depend a lot on your specific cluster, right?
Yeah, I understand. That would mean we double the amount of histograms we have per resource.
Yeah,
which is already a pretty huge cardinality as is.
Yeah, but I think we should also drop stuff like content type and client.
Oh yeah, for sure. Yeah.
But then we just buy ourselves a lot of space, right? Like these are unbounded dimensions that are just basically not. So yeah, I mean, like if we clean these things up,
I'm still not totally convinced that that is necessarily the better thing to do rather than a per webhook histogram or a summary even.
I mean, I would generally say that each component should have its own SLOs that are, or have its own signals as to whether that component is performing correctly. So in my mind, like, yes, you should add metrics to your webhooks so that you know how they're performing, but I do think it's also quite useful to have a signal just to see if the API server is doing its job correctly.
Yeah, I mean, it's kind of hard to tell right now is the thing. Like it's actually basically impossible to tell if it is a conjunction of webhooks or if it's internal API server, and it takes a lot of digging and grepping through logs to figure out whether or not, like, you know, what something looks like during one request pass. I mean, it's yeah, it should not be that hard.
This is hopefully also something tracing will help with.
Yeah, I agree, actually. I agree.
Yeah, definitely.
Okay, yeah, I just wanted to put it out there. It's something I mean, it's not something I have an answer for. I just was curious what people thought about it. I will continue to think about it, and if anybody has additional thoughts on it, then.
I definitely think the intention is very good. I think there are a couple of solutions that we could go with. Yeah.
We still have another thing on the agenda, so we should let's skip the sweep through the PR backlog. And Alexander, do you want
to? Yeah. Can you guys hear me?
Yeah.
Yes.
Okay. Awesome. Let me try to share my screen. For some reason I can't share my screen. It says the host has disabled.
Oh, how do I do that?
I think I recall in SIG we always have to make people co-hosts. I don't remember if we have to do that here.
Or I can just forward. Well, would the.
Okay, I made you a co-host, so you can.
Okay, perfect. Wonderful. All right. Okay. All right. Thank you. Thank you so much for giving us an opportunity to come and talk to you guys about static analysis and dynamic analysis. So my name is Alex Chernyakhovsky, and here today with me I have Patrick. We're both part of the GKE security team, and we've been working on trying to solve the problem of reducing the possibility of leaking potentially sensitive information like credentials to logs. And in the next 15 minutes, we will try to hopefully clear up some of the questions that were raised during the review of the CAP that is currently under the review that proposes extension to Klog to inject a hook which will allow us to inspect the data before it goes into the logs. So here's our agenda. As I mentioned, the objective is today to, there were some very good questions that were raised as part of the CAP. One of the questions was, why cannot, like concretely the question was, do we need to actually extend Klog, which is a core component of Kubernetes, and a lot of other components in the ecosystem depend on it? Why can we not just use static analysis, which does the scanning completely outside runtime and get similar results? And just sort of TLDR here, we believe that we should do both. And as a matter of fact, in this CAP, we decided to purposely focus on the dynamic analysis, just the Klog extension. And our plan is to follow up with another CAP that will propose adding a pre-submit check to Kubernetes that does the static analysis. But as you will see, and hopefully we will be able to explain this, that for the best results, we should focus on both types of analysis, dynamic and static. So, excuse me. So I will explain how we do static analysis. We also do a short demo of the tool that Patrick and we've been working on. That we actually been running against Kubernetes and actually found some leaks already. So we're hoping that we can continue to provide value to Kubernetes through this tool. Then Patrick will talk about dynamic analysis, and we'll talk about what we recommend going forward, and hopefully we'll have some time for questions. So as I mentioned, static analysis is something that we consciously decided not to include in this CAP, just to make sure that we have a actionable outcome from this CAP, where we want to add a possibility to inject additional processing into the Klog, and this processing will take care of detecting potential leaks. And it is our intention to follow up with another CAP for the static analysis. So when we talk about static analysis, we actually talk about a specific type of static analysis that is called tame propagation analysis. So tame propagation analysis is based on the idea of identifying sensitive pieces of information as they enter the program or a function, and tracing its potential flows through the program. And in particularly, we're interested in the events where this potentially sensitive data exits the boundary of the program. So for example, such boundary could be a log, or it could be a database, or it could be an RPC call, or an HTTP outbound call. And in the parlance of tame propagation analysis, this sensitive piece of data, we call it source. And this moment in time when this data leaves the boundary of the program, we call it a sink. And basically, the idea of the tame propagation analysis is very simple. We build a graph of the program, and we first find the inputs, and they become sort of the root of the graph. And we trace all the execution paths until we find a sink. And we also have this concept of a sanitizer. So it's not always bad that your sensitive data basically ends up in a sink. Basically, it is not bad when there is some processing done ahead of time which removes the potentially sensitive data. So in other words, there is another concept of a sanitizer, and if the sanitizer is invoked just before we reach the sink, basically this is considered a normal code flow, and we do not raise any concerns about that. So probably as you're thinking about this, there are two parts to this. One part is the analyzer itself, and sort of the sort of graph processing, et cetera, but you're probably already thinking in terms of, yes, this requires a lot of domain knowledge. Like for example, I could be the best static analysis developer in the world, but But unless I know the types that may contain sensitive information in Kubernetes, my analyzer will not find anything. In other words, there is certainly significant input that is required from the community to describe the inputs that may contain potentially sensitive information. And the same goes for the sanitizers, and the same goes for the log, which pretty much kind of explains the main architectural characteristic of the analyzer, that it is very config driven. So it receives a config that defines all the sources, all the sanitizers on the logs, and then when it analyzes the graph, it makes the recommendations about potentially risky operations. So there is another aspect there's another interesting complexity about this analysis, is something what we call propagators. So like pretty much the same picture here. You see the input, but then we took the input and we converted it to the string. So we basically, let's say, imagine that the input is a Kubernetes secret, and we call the string method on it, and now the variable s is a string that contains credentials. Now, at this point in time, we now have several inputs that contain confidential information, and we need to make sure that we properly handle all of those sources. So I think this is pretty much all the theory we need to understand how the static analysis works. With that, I will pass it over to Patrick, and he will do a short demo of the tool we've been working on.
Yeah, hello everybody. But yeah, if you could hit me with co-host as well.
Yeah, I'm stopping.
I would also like to share my screen if I may.
Oh, yeah.
Here we go. So share screen. Here we go. All right, cool. So yeah, pretty much exactly like what Alex was saying. We did end up finding one live in the wild Kubernetes example here. We are in the kubelet token manager. And like primarily, I always think of these static analysis tools as things that are like helping carry developer mental load, because here we have like just a token request refresh, and there's a very simple case of if the requested expiry is nil, that's like an invalid request. So we're gonna just throw this into a log. Hey, this request wasn't valid. Figure out what's going wrong. But in this particular case, we have this token request is defined over here in the top right as containing this status, which is optional, but that request itself might contain this token. So this is one of the instances where it's like, yeah, this is maybe something we should have explicitly removed a token. We don't know if it's there or not. This may have never actually become an issue. But here, back at the end of April, we ended up rewriting this to explicitly zero out that token before it was sent to logs. But this is the sort of thing static analysis is great at checking or catching. So here we can use our vet tool and see that it's telling us that right here we've got this issue. And the big one, like Alex was saying, is catching tape propagation. So here, if we were to specifically say, cast this thing to a string first and log that, make sure that we're still catching things like this as well. So we do have, oh, sorry, go for it.
So we're actually out of time.
Oh, okay. Well, so like the 2-minute wrap up is that the interaction with the existing cap would be this kind of, the dynamic portion of analysis inverts the whole bit, where instead of trying to find where input can possibly reach, we are looking at the point of logging what input is coming in. And we are able to integrate our sanitizers into that to identify data is coming in, probably using reflection. But yeah, it's a hard problem, and I think best results, you should use both. Certainly knowing what sorts of things to look for in static analysis depends fundamentally on what developers are doing. And without any signal of what static analysis, like false negatives, you are allowing through, there's not really a great way to iterate on that without having something in the dynamic on the runtime side saying this is what you're missing. So yeah, that's my 2 cents.
I think we should probably talk more about this.
Okay.
I would also like Merrick to be here because Merrick has just done the static analysis bit for instrumentation recently. So, yeah, I think it sounds reasonable to me. But we are out of time. I am so sorry. And I know alarms going off. Anyway, should we just put you first on the agenda for next time, or?
That would be great. That would be great.
Yeah,
okay.
Let's do that.
Okay, let's do that. Okay, well, stay safe, everyone. Sorry for going over on time.
All right.
Thanks, everyone.
Thank
See
you
next time.
Thanks.
Bye-bye.
Bye.
See you. Bye.
Bye.